this video, we're going to do some worked examples, and we're going to have a short discussion on problem solving as we go through. This is the more traditional way that people think about physics, solving problems using algebra and exact mathematical solutions in order to describe physical systems. The first one we're going to start with is what is a one-dimensional example. In this case, that one dimension is on our y-axis. We have a gymnast here. The weight of the gymnast is pointing downwards, as weight does, because weight is the force of gravity. And then they are being supported by the interaction between their feet and the floor. Because they're a gymnast, they have this wonderful, perfect posture, so that their weight is distributed evenly between their two feet, so that both feet is experiencing a force S on the soles of their feet, pointing straight up, that are balancing with this force W. So, the mass of the gymnast is given in the problem as 40 kilograms, and we're going to find W, and we're going to find S. So we begin by finding W. W is equal to the weight, so we assume the direction is down, because that is the direction that gravity acts. And the magnitude of the weight is going to be given by m times little g, the acceleration of gravity. And I have written that out here, and the answer there is 392.4 newtons. It is, the unit newton is the product kilogram times meter divided by second squared. It comes from multiplying the mass times the gravitational acceleration of the person due to the fact that in this case they're standing on Earth. In the future we'll just abbreviate Newton with a capital N, while kilograms, meters, and seconds are what we call base units. The Newton is what we call a derived unit. So we're going to now find S, and we're going to do that by applying the linear equilibrium condition from the earlier videos. The sum of the forces acting on the object has to be equal to 0. So in this case we have W, the weight, plus the force on the sole of one foot, plus the force on the sole of the other foot, has to sum to 0. That's part of the application of the equilibrium condition. We found the weight earlier, it's 392.4 newtons, and it is in the downward direction, which we will symbolize by calling this negative 392.4 newtons, plus twice times the force on each individual sole. We can rewrite this now. We can do algebra. We move the 392.4 over to the left side of the equation. That leaves us with 2s on the right side of the equation, and we divide by 2 so that we find that s, the thing we're looking for, the force on each foot, is 392.4 divided by 2. And since down is negative, the fact that this comes out positive means that it's upwards in the opposite direction of the weight. In this picture, we have a small teddy bear with 3 forces acting on it. The 30 Newton force, which is in this diagram pulling up and to the right, the 40 Newton force, which in this diagram is pulling directly left, and a 40 Newton force, which in this diagram is pointing towards the bottom of the screen. We're given that the mass of the teddy bear is equal to 0.5 kilograms. In order to find the net force on the bear, we need to define a coordinate system, then find the components of our force vectors in that coordinate system, and then sum the components to find the net force. So, our coordinate system that I have chosen in this problem has the 30 Newton force pointing upwards and to the right, making a 45-degree angle with my positive x-axis. The 40 Newton force pulling to the left in this picture is directly on the negative x-axis, and the 40 Newton force is pulling in the negative y direction. So I made these choices for simplicity. There is actually one choice that would have made the problem a little bit shorter, but I chose this one for a reason I'll mention when we get to it. This one has two of the forces lying exactly on the axis, and this generally makes our life easier for a reason we'll get to in a second. We need to find the components of each vector. The components of this first vector, which I'll call vector A, are 30 newtons times cosine 45 in the I direction, in other words, parallel to the positive x-axis, plus 30 newtons times sine 45j, in other words, parallel to the positive y-axis. And again, our unit for force here is Newton. Vector B, which I have labeled as the vector pointing parallel to the negative x-axis, has a negative 40I and 0j. It has no y direction component. It's on the negative x-axis. So the vector B reduces to components of negative 40I newtons. By a similar sort of argument, this thing which I will label vector C has a 0 component in the I direction and a negative 40 newton component in the negative j direction because it lies on the negative y-axis. At this point, we need to add the individual components together. And when we do that, for the x direction, we get negative 18.79 in the I direction and negative 18.79 in the j direction. So the net force is going to be down and to the left in this picture. Thinking about this, imagine 3 children having a tug of war over this teddy bear. One of them is pulling up and to the right, one is pulling to the left, and one is pulling straight down. The left plus down are going to overwhelm this force that's up and to the right, and it's going to cause the bear to accelerate downwards and to the left. We can use the Pythagorean theorem to find the magnitude of that resultant force, which is going to be 26.57 newtons. And we can find the angle, which is going to be 225 degrees from the positive x-axis, which is how we know it's going to be pointing downwards and to the left. The acceleration of the bear, the thing we are looking for, what's going to happen to the bear, is that the net force divided by the mass is going to be equal to the acceleration. So 26.57 divided by 2. I'm sorry, not 2. Divided by 1/2, 0.5. And that's going to be equal to an acceleration of staggering proportion of 53.04 meters per second squared. The last of the worked examples that we're going to have in this set has a 500 Newton crate hanging from a cable that has another cable pulling up on the center of that cable. So the first thing we're going to do to solve this thing is we're going to draw a free body diagram and then do the geometric analysis. So here is a picture I made of the free body diagram. These two little angles here are both 40 degrees from opposite interior angles, which we discussed at the end of the previous video. So this angle is going to be negative 40, and this big angle is going to be 220. Because of the structure of the formulas that we used in our sort of general formulation, we want to use angles that are measured from the positive x-axis. So on our free body diagram, the angle to the first tension is going to be 90 degrees, the angle to the second tension is going to be 220 degrees, the angle to the third tension is going to be negative 40 degrees. We're again going to apply the equilibrium condition to the components of the vectors so that the net force in the x direction is going to be 0, which is going to be equal to the sum of the x components. So T1 cosine 90 plus T2 cosine 220 plus T3 times cosine of negative 40. And similarly for the y components, we're going to have 0 is equal to T1 sine 90 plus T2 sine 220 plus T3 sine negative 40. T1 is equal to the weight, which is equal to 500 newtons, and T1 points only in the y direction, which makes our calculations a little easier. And note that that's going to come out of this multiplication, since cosine 90 is 0 and sine 90 is 1. So when we plug that into our equation, we have 0 is equal to 0 plus T2 cosine 220 plus T3 cosine negative 40, and 0 is equal to 500 plus T2 sine 220 plus T3 times sine of negative 40. You would then use your favorite method for solving two equations with two unknowns to find the values for T2 and T3, and it turns out that if you do that, which is left as an exercise for you, those two magnitudes are equal, and equal to 388.83 newtons. So those are the worked examples that go along with this chapter.